Hey everyone, welcome back, and today we're going to be looking at the number 9 question on the Chapter 10 practice test. Now this is a find the interval of convergence for this series, and for all of these questions where you find the interval of convergence, the first thing you should do is double check and make sure that you're looking at a series, if it's a geometric or if it's not a geometric series. Now if it's a geometric series, things get really easy for the interval of convergence. And if it's not a geometric series, of course, things are a little bit more difficult. So let's write out the first 4 terms and see if this is actually geometric. Well, that certainly doesn't look geometric to me. If you're not 100% sure, you could also simplify this again. So in particular, the sequence in the denominator doesn't look very geometric. In other words, to get from one denominator to the next, we're not just multiplying by anything. There is an actual, as it turns out, an arithmetic sequence in the denominator. So no, this is not a geometric series. We have to use the ratio test in order to find the interval of convergence. And whenever we use the ratio test, don't forget to check the endpoints. Now for power series, we set up the ratio test with the reciprocal of the nth term. So we have the n plus 1th term multiplied by the reciprocal of the nth term. And we automatically set that less than 1 because we want to basically solve for values of x. So we need to make this an inequality that we can solve. Also, we need to put the ratio into absolute values since the ratio test only works on positive terms. Replace all of the n's with an n plus 1. Make sure you do that in parentheses so you observe good algebra. And then multiply that with the reciprocal of the general term. Now we're going to do some simplification here to make things a little bit easier. Firstly, we're going to re-express x minus 9 to the n plus 1 power as just x minus 9 to the n power multiplied by x minus 9. And then we're going to simplify the denominator of that first fraction. Now the x minus 9 to the n power, those are going to cancel out. And then this x over x minus 9 piece, that doesn't have any more n involved with it. So actually it doesn't need to be in the limit anymore. So we're going to take it out of the limit, but we're going to make sure that it stays in absolute values because you can't really get rid of that. And then now inside the limit we can simplify. And then now in that limit we will divide everything by 2n. Or no, we'll divide everything just by n. That's enough. And then simplify. And then now it's easy to see that this limit as n approaches infinity is going to be 2 over 2. And that limit is just 1. Now what this last statement says is that the limit of the ratio is the absolute value of x minus 9. And if the absolute value of x minus 9 is less than 1, then the series is going to converge. Like every power series, we're going to compare that to x minus center is less than the radius. So the center is 9, and the radius is 1. So the interval of absolute convergence is the interval from 8 to 10. And at x equals 8 and x equals 10, the ratio test is actually inconclusive. So we're going to have to do something to check whether or not the series is going to converge at 8 and whether or not the series is going to converge at 10. Now the typical way to do this is to substitute 8 and 10 into the series. We're going to start by checking the endpoint x equals 8. If we started off with x minus 9 to the n over 6 plus 2n, we substitute to get x minus 9 to the n on the numerator, which simplifies to negative 1 to the n over 6 plus 2n. Now we're going to write out the next few terms, the first 4 terms of this series, just to see what we're dealing with. And then we're going to simplify, and we see that what we've created is an alternating series. Now, the correct way to check whether an alternating series is going to converge is with the Leibniz test. Now, in the Leibniz test, we check the limit of the absolute value of the terms. For us, that means we're going to take the limit as n approaches infinity of -1 to the n over 6 plus 2n. Now, the only part of this general term that makes our general term negative is this -1 to the n power. So what's commonly done is we'll just go ahead and replace that with 1. And now we have a series, we have positive terms. Now, as n goes to infinity, our limit is 0. And for Leibniz test, this means that the alternating series of -1 over 6 plus 2n converges. Now be careful, because the Leibniz test looks a lot like the nth term test, and it's easy to confuse the two. Make sure you know which test you're doing. Furthermore, we know that our series that we started off with is going to converge when x equals 8. So we've tested our first endpoint, x equals 8. Now we've got to check our next endpoint, x equals 10. So we're going to do something similar. We're going to start with the series again, and then we're going to substitute 10, and then simplify. Now that we're simplified, let's check out the first few terms of this series. Okay, this is not an alternating series, and so we're not going to use the Leibniz test again. But looking at the general term here, that 1 over 6 plus 2n, that's really close to a p-series. So when we have a series that's close to a p-series, we're going to use the limit comparison test, or the LCT. For this test, we're going to compare our close to a p-series to an exact p-series that's closest to it. So this p-series, I should say this, the general term of this p-series, 1 over 6 plus 2 to the n. Well, that's close to, we're just going to get rid of the 6 part because it doesn't have n in it. And then we don't really need the constant multiple 2, so we'll just get rid of the 2. And we've created the closest p-series, 1 over n. Now we just have to examine the ratio of our two series and take the limit. I always like to put my p-series on the denominator, and well, that's just habit. So we got 1 over 6 plus 2n over 1 over n, which simplifies to n over 6 plus 2n, which simplifies to 1 over 6 over n plus 2, which this limit we can actually know it's going to be 1/2. So we have a limit from the limit comparison test. And what this tells us is if we get just any old number on the limit comparison test, that means either both series converge or both series diverge. But we know something about the series 1 over n. We know that the series of 1 over n diverges. So that means our series 1 over 6 plus 2n also diverges. And of course, our original series, or the series with, our original series will then also diverge when x equals 10. So now we're ready for our conclusion. Our series x minus 9 to the n power over 6 plus 2n, well, it's going to converge absolutely for x between 8 and 10, and it's also going to converge at x equals 8. The series doesn't converge at x equals 10, so we're going to keep this a half-open interval, and this, the half-open interval from 8 to 10, including 8, not including 10, is the full interval of convergence for the series. Now I know what you're saying. That was a long problem. Luckily for you, probably, if this is the only question, if we have to do the entire interval of convergence, that's the only thing you're going to have to do for a question, because it is time consuming. So that's finished, and we'll see you for the next video. Have a good one.